Was that? All right, cool. So, all right, welcome everyone to our first in-person and live Grid.ai meetup. We're going to be talking today about scaling production machine learning without the MLOps overhead. And I'm going to take a step back to just introduce myself to everyone. Some of you might know me who are watching virtually, but for others, it might be the first time. So my name is Ari Bornstein. I'm originally from the Washington, D.C. area, but I've been living the past 5 years in Tel Aviv. I did my undergraduate in Baltimore, double majoring in history and computer science. After that, I started out in New York, worked with Microsoft in mobile machine learning development for about 7 years, working in the fields of AI and developer advocacy. And during the past 2.5 years, I started doing a master's program at Bar-Ilan University in their natural language processing lab, where I did my thesis on cross-document co-reference and semantic modeling. And then about, say, 7 months ago, I started here at Grid.ai to head up developer advocacy and to spearhead our efforts to try to help democratize AI and reduce boilerplate across both code and now IT and infrastructure as well. So to get back to the main topic at hand, what we're talking about MLOps, one of the things that I've noticed based on the research work when I'm in the research lab and when I'm talking to developers, today the majority of ML research starts locally. And that doesn't necessarily mean that like it's just running on a laptop, but it might be running on a local hosted VM or a local hosted notebook instance or a local hosted even like a local instance of a research server. And what that means is that you have kind of control over your environment. You can get stuff to work, you can fine tune it, you can get your research, but there's a challenge when it comes to actually building state-of-the-art models or models that actually get top performance. You need to be able to scale, and today that's really hard. And the real reason that we need this kind of scale is we need it for a couple of reasons. One is, as teams, we don't work independently, we collaborate. So we need to be able to work across stakeholders. Here at Grid and PyTorch Lightning, for example, we have 35 employees distributed all over the world, and we need to be able to share experiments, share results, and collaborate. Additionally, we need to be able to manage distributed compute, distributed data, and there's a lot of overhead in making sure that infrastructure scales and is optimized. We need to make sure that this hardware and this infrastructure is fault tolerant, and there's a lot of energy that typically goes when you're thinking about scaling into making that happen. And you need continuous integration and continuous monitoring, because at the end of the day, when we're talking about machine learning, it's not a static process. We can train a model, but the model that we have today, our data changes and we're modeling dynamic processes. So we need to constantly be able to refine, update those models and improve the results that we have. Otherwise, we have data drift and our models don't perform. So a perfect example of that would be if you were to look up to build a natural language processing model about 3 years ago, and you came upon the term with like a word embedding, corona, might have a very different connotation than that word in 2021. So the way that most organizations over the past 5 years have started to attack this problem is through MLOps. And the process of machine learning operations was created to enable scale. So the idea of MLOps is that we have it's inspired by a lot of the work that was done in DevOps to enable software to scale. And the idea is we have machine learning, let's break it up into individual parts of a pipeline, and let's work with tools that enable us to orchestrate and work in teams and distribute out the entire machine learning process. So for example, we might have the data pipeline, and there we have our data engineers and our data scientists and our data warehouse and SQL administrators and analysts working to generate the data. And then we have our dev teams, and those might have within them research teams and data science teams. They might have machine learning engineers in them. They might have people who are edge engineers and working on refining stuff. And we have a lot of work done actually on the model. And then we shift one more step, and we actually have this is where like the IT and the operation teams come in. So we need to think about how do we do deployment, how do we scale with things like Kubernetes, and how do we actually, sorry, we have one person coming up, we'll look them up, but how do we scale our models? And then after that, as we said, this is a dynamic system. So we need to monitor our models in production and constantly cycling this. So there's a lot of advantages when we think about MLOps versus local deployment, because this enables us to scale. This is what enables us to get OpenGPT-3 multi-billion or trillion parameter model that gets state-of-the-art results. This is what enables fair to be fair, or Google Labs to be Google Brain to be Google Brain, or the state-of-the-art research to be state-of-the-art research. But there's a challenge with this, is this MLOps process, because it's so complex and it's divided across so many different stages, because we've tried to separate it out, as we scale, it adds complexity. And there's 4 areas of complexity that I've seen in my experience during my time at Microsoft, and also working with developers and hearing and speaking with companies that kind of slow that impact the machine learning process. And so the first one in my experience is iteration time. As you have this complexity where you create a model, you have dependencies based on your person who's generating the data to pass it off to you. You need to iterate the model. You need to maintain all this stuff. Then it needs to go to the IT person. And there's this whole communication cycle that just slows down iteration time. Additionally, if you're not properly configuring each of the steps of your pipeline, the iteration time of a model can take, at best, hours or days, at worst, months to iterate models. So a lot of the effort then goes to how do we deploy the models, or how do we focus on data, because we don't want to worry about experimentation with training. So iteration time is one of the key bottlenecks. The next is data access. How do we optimize our data? For me, when I was at Microsoft and also working across people who've worked with multiple clouds, the amount of times I saw people misconfiguring how they use blob storage or S3 or Google to just upload their data and pull their data, but not using storage that's optimized for machine learning training, and all the configuration that goes to that slows down iteration time. So how we manage data access, how we ensure different people across the teams have only the right people have access to data, and how we make sure that the data, where the data is stored, is optimized in a way to make sure that we can iterate our models as fast as possible. Critical bottleneck when we think about this whole MLOps lifecycle. The next thing that really bogs things down is dependency management. So this has to do with, by the way, welcome. So I'm talking a little bit right now about MLOps, and I just introduced the concept, and we're talking about some of the complexities. So the first one was iteration time. The second one is data access and making sure that you have optimal data configuration so that your models train fast. It's very, there was one example where I saw somebody spend something like $300 to train a simple speech command model for a Raspberry Pi, because he chose like just a standard, the cheapest blob storage that he could. And because it wasn't optimized, wasn't even using SSD, like the iteration time on one cycle was something like 4 hours, 5 hours. So like an epoch. So he ended up burning through something like $100, $200 on compute on something that should have cost $5 because of that. The next layer is also dependency management. So this comes into reproducibility, making sure that when you take your code, that dependencies don't change. In open source, we have a lot of dependency chains. So I might have code that runs one day because I have all my conda configuration, pip files, pip dependencies in my requirements file, but then something changes on one of those dependencies, or something changes in the environment, and I go to reproduce my model, rerun the iteration cycle, and I constantly, models and code is breaking because of that dependency management. Also being able to just take code, run it, and get all those dependencies linked up in the first place is a big bottleneck of modern MLOps. And the last big challenge is there's a lot of tools out there for MLOps, but there's a big challenge in terms of lock-in reproducibility. A lot of the tools that exist come in the form of APIs that you have to integrate into your code base. And once you start integrating them into your code base, your code kind of gets locked towards those solutions and those platforms. And then that means that in order to reproduce, like if you want to reproduce it on a different system or a different place, you have to gut the code that's related to one MLOps tool, and that reduces your flexibility. It also means that the work and your ability to collaborate across different organizations and teams is very, very difficult. And if we take a step back, like I think this is one of the big factors of reproducibility crisis today is the current way that we design MLOps tooling and MLOps tools kind of is designed for vendor lock-in in a way that's not conducive to reproducibility. And it's not even intentionally about vendor lock-in, but it's also just the complexity of creating the cycle. So that's why, like, for example, when you have an OpenGPT-3 model, you might, or even better, there was there was the DALI model that was published recently, and then and by OpenMind, and then afterwards they open sourced the code, and they open sourced an autoencoder, and there was a lot of other code. Now again, can't speak for DeepMind, and I don't know exactly what happened behind the scenes, but my guess is part of the complexity of why they can't just release all the code is not just because of the complexity of the code or because they want to keep everything in-house. It's actually because to release that code, they probably have to decouple and refactor so much of the code that's specified and hard-coded to their own internal systems that they can't open source it and share it with the wider community, even though that's like one of their objectives, right? And that's conjecture. I can't speak for them, but I think based on my experience working with research labs and seeing how research code is developed, that lock-in with proprietary tools, internal tools, and self-made tools kind of really impacts our ability to do reproducibility, have the iteration time, ensure that we have optimal data efficiency, and manage dependencies so code just runs. So I think this is really critical because at the end of the day, when it comes to faster ML, more performant models, models that get us to where we need, research iteration speed is the key to everything. I like to say, like, the parallel for me is if we think back 10 years ago, 15 years ago in software development, when we were using compile time languages like Java, C++, again, there's a lot of value in those languages in terms of being able to have more efficient models, to have lower, closer to the hardware infrastructure code. But think about the amount of time it took to compile, and then you compile code and you realize it's because you forgot a semicolon, you'd get this error after, at syntax time, even though it took a while to compile other DLLs to get to that error. And it slowed down software development. But as things have changed with prevalence of more interpretive language like Python, like JavaScript, it enabled us to develop code, go from ideas to something that we can actually tangibly use much faster. And that iteration speed has driven the whole industry forward, including models that are built on top of lower level languages. And we can see that in other areas as well. For example, if you look at Rust today, that type of methodology that does that right balance of iteration speed really helps move entire industries forward. And I think this is a major bottleneck for machine learning, because if we can optimize the iteration speed, that means that we can experiment faster. It means that if we have a huge bottleneck around data labeling or how we come up with techniques for doing data experimentation, we can kind of A/B test that around how we train models. But because today, the amount of time it takes to retrain a model or orchestrate a model or do all of this, it means that we don't have that flexibility. So we need to make critical assumptions when we're generating our data or pre-processing our data and cleaning our data that turns training, and training becomes our bottleneck, even though if we think data is our only bottleneck. So I truly believe that iteration speed is the heart of better ML. And what's interesting about attacking this problem, and I also believe that MLOps, while it enables us to solve this problem of being able to scale so we can get state-of-the-art results, traditionally right now it's come at the trade-off of slowing iteration speed. And I think what's interesting is, and part of the reason I joined Grid.ai and PyTorch Lightning is a few years ago, not that many, like 3 years ago, deep learning had similar problems, and it came in the form of boilerplate. So who here in this audience knows what boilerplate code is? Okay. All right, I'll just explain it anyways. It's on the slides, but there's certain code that you re-implement all the time in different ways. There's no standards for it. It gets implemented again and again, and it can lead to huge engineering bottlenecks that slow down what? Iteration time. So when it comes down to, so the standard dictionary definition of this is exactly that: complex, repeatedly rewritten code with little to no functional variation. And what this leads to is it leads to, again, code that's hard to reproduce, because I might have an implementation that runs, for example, on a GPU, right? So I use CUDA, and all my tensors have .CUDA on them. And now I want to run that on an edge device that's running with CPU, and I have to manually delete the .CUDA from every single call. All of a sudden, am I going to reuse that code? Probably not. I'm probably going to start from scratch, and that slows iteration time. The code becomes hard to reuse for that reason, and it becomes harder to debug because you don't necessarily know exactly where all your code is. You can rename these, because each of these patterns can be re-implemented in many different ways, and they can be implemented in many different parts of your code base. It's really hard to track them down, track the implementation of where certain functionality of your code is implemented. It becomes hard to track it down, and it makes things hard to scale. Again, for exactly that reason, because now if I want to go, let's say, from a GPU, a .CUDA device, to a .TPU device, imagine the overhead of having to refactor the code. Now I'm on a multi-GPU device, or I want to use the latest innovations with frameworks like DeepSpeed or Scale. It means, again, I have to refactor my code to implement that. And now what happens when I want to share that code, right? If you don't have a cluster that supports DeepSpeed, but I needed DeepSpeed to train this huge model, you're not going to be able to experiment or play around with that code. So one of the things that helped drive the development of PyTorch Lightning was these questions of what if. What if instead of being hard to reproduce, was self-contained, and so all the elements that were required to run your code were part of the actual module. So instead of viewing your code as just a graph, your model is just a graph with weights, it's also the graph with weights, but it's also the transforms and the splits that you need. And on top of that, it's all the hyperparameter configurations. Those are all incorporated, encapsulated in how you configure your model and data, so that then you can export that, and that's portable. What if instead of code being hard to reuse, your code was modular and standardized and organized, so you know exactly where to look when you need to debug things, but also on top of that, when you need to override stuff, you don't have to rewrite your entire model class and all your model logic. You just have to override the individual functions that you need. And the last thing was, I'll skip hard to debug because we said organized and if it provided logging and visualization. But the last thing was, what if instead of being hard to scale, because of the way we encapsulate and abstract out infrastructure, we can decouple the hardware that your code runs on from your machine learning and deep learning code itself. So this is what PyTorch Lightning does. It's essentially, the tagline of PyTorch Lightning is it's organized PyTorch. It provides a set of interfaces that you can implement these, you organize your code, implement these interfaces. And once you've done that, because your code fits inside these interfaces, all of this functionality that is boilerplate functionality is provided out of the box. So you get it for free. When there are new state-of-the-art developments, things like DeepSpeed, things like a new PyTorch profiler, instead of you now having to tack that into your code, you can access it directly from a trainer flag. You get access to these features right out of the box. Additionally, because everything is modular and encapsulated, that code's easier to reproduce, scale, and share. So there's a couple key core design principles about Lightning, and we're going to talk about how we can apply some of these same principles to MLOps in a minute. But the first is this concept of self-contained data models. So we want to make sure that we can mix and match our data models. So I have one data module that contains all the information that I need to load data for ImageNet. that should be, and I have another one for Reddit data, because they implement the same interface, they should be interchangeable. They shouldn't be hard-coded or tightly coupled with my implementation. Code should be modular and decoupled. So imagine our standard deep learning code with our training loop. Here, what we do is we would decouple out our research code into our Lightning module. The data code goes in our data module, and all the engineering code behind that, the things like logging, the things like your optimizer.step, the code that's the most error prone, or your boilerplate code, this code, your .evals, your .backwards, your .tokudas to XLA, this goes away, gets managed for you by the trainer. And then at the same time, we want to make sure that you have full flexibility. Because if we just abstract things out for you, but then you have no way to change them when you need to, then it's not very useful. So a key aspect of any solution is this flexibility. You want to be able to override what you need. So instead of having to re-implement everything, you just override the functions you need. So what does this enable? This enables you, as we said, to get state of the art and also to scale. So for example, we have code, it runs on a CPU. We want it to run on GPU, we put GPUs equal 1. We want it to run on 8 GPUs because we're now running on a new device that has 8 GPUs, just set GPUs equals to 8. If we want to run it on 32 clusters, each with 8 GPUs, easily scale that as well. And now if there's additional configuration you need to do for your cluster to set this up, we have brand new documentation posts that I can share afterwards that explain exactly how to do that. So this enables things like distributed training, but you can also play with and integrate very quickly with all the different state-of-the-art approaches, whether that's data distributed parallel, or AVOD, deep speed, or fair scale. You have all these different accelerators, and what's nice about this is instead of you actually having to modify your training code, this is completely decoupled. So you get these integrations out of the box. If you want to add your own, you have interfaces that you can implement and contribute. So additionally, you get things like checkpointing. So when you're training, automatically in every epoch, it's configured to checkpoint your code. So that way you can share and quickly evaluate. You get things like being able to integrate with experiment managers and loggers. And when it comes, and there's many, many, many more features. I'm not going to go into all of them now. If there's questions afterwards, I can talk about them. But I think I want to take this back into the larger conversation about machine learning and MLOps. So today, there's this huge dependency between machine learning and MLOps in order to enable scale. And we talked about most solutions today do so at the cost of flexibility, at the cost of iteration speed. And so our question is, just how you saw Lightning decouple the engineering code and this complexity of the engineering code that gets in boilerplate, that gets reproduced again and again and again from your actual research code, what if we could decouple the machine learning infrastructure from the machine learning ops process? So you have the flexibility when you need it, but when you want, things should run more or less out of the box. And that's kind of this idea of what we do at Grid with the Grid.ai platform. We provide three solutions, and there's a lot being developed. Things are changing all the time, so it's a really exciting time to be in this field. The first offering that we have is this offering around data stores, which enable you to upload data. And as we said before, data becomes a big bottleneck if it's not properly configured. Well, these data stores are optimized for making sure that your models train fast, so that you don't have that situation that I was telling you about of the person who's spending $100 to train something that should cost $5 because he chose the wrong data, the wrong S3 blob type when he uploaded his data, which wasn't in the documentation, right? Or maybe it was, but who reads that documentation when you're the ML engineer, right? So the other advantage of data stores, and talk about it a little bit as well, is that in your code, instead of you actually having to download your code from blobs every time you run, they're mounted. So you access these exactly like you access your local device, so you have that full flexibility. So yeah, that's exactly what this is talking about, fast loading. The next thing that we have is your entry point, which is sessions. So sessions are just compute that's optimized for machine learning workloads. They come pre-installed with all the packages you know and love, your PyTorch, your TensorFlow, your Keras, your PyTorch Lightning. On top of that, they already are pre-configured for with Jupyter Hub, and you can launch and access them through remote SSH, through Visual Studio Code or your any IDE of choice. The other advantage of these sessions as well is that like they're fully integrated within GitHub. So I don't know if you guys have ever had to do that before, where you go to run something on a cloud device and you want to clone your code, and then you get this error. So you have to go to GitHub, and then you have to create a new key, and then you have to manage the key. Because of the way that the Grid platform integrates directly with Git and GitHub, you can actually just run, and because you've logged in and authenticated through GitHub, all your code will run directly as if you were logged into your account. And you have all these things that I just said. Standard pause run. And then when it comes, and the goal of the sessions is inside a session environment. That's where you take your Lightning code or whatever the code you have, you experiment as if you're on your local machine, you get your code where you need it to be, and then you scale it with runs. And then runs, what runs do is they enable you to scale. You can leverage spot instances with, it's probably going to be in the next clip. You have all these things that we're talking about in terms of accessing your data optimized. You have the GitHub integration, but you also can run this code if it runs in your session, and you can then scale it to, if you can get it to run in the session, you can then scale it to the run, and you don't have to add MLOps code into your code to make this run. So unlike a lot of these other solutions where you actually have to go and import like I won't say names, but import like MLOps tool A, and then call MLOps tool library in the SDK in order to actually orchestrate your runs. Grid is designed to enable you to scale those runs directly through Git and process anything like the IO channels on it. So this enables like you to scale, and then like most standard platforms, you get the visualization. You can monitor metrics within the Lightning ecosystem as well. We have a really cool open source library called Torch Metrics, so which has new metrics being implemented every day. What's cool about Torch Metrics is not only do they provide you metrics implementations, but they're all differentiable implementations, so they can be distributed across GPU. So I don't know if you've used like scikit-learn metrics in the past, which is awesome. I personally am a huge fan of it, but one of the bottlenecks there is when you want to scale across, build gigabytes or terabytes of data, and then you want to actually run it becomes very, very slow because it's CPU driven. So because these are tensor-based, it's a tensor-based metrics library, it enables you to scale with your code. And then you can, because of the way that this reads from however whatever logger that you use, like TensorFlow logger or the rest, you get those visualizations right out of the box. So from here, I don't want to go, I can do some demos, I can walk through, I can do a lot of different things, but I'd rather take a step back and answer any questions. If there's questions in the chat, questions from you guys, we can talk about Grid, we can talk about challenges of MLOps, we can talk about Lightning, or some of the really cool work that we did this week with Flash, whatever you want. I'll open up to you guys.
I just wanted to ask, like, so my experience with PyTorch Lightning has been not much, but with research, like, what are the capabilities with research? Like, when you're working on it, you're trying to see how an algorithm works in like different cases and how you can combine two different ideas together. Like, so how flexible is that PyTorch Lightning with that?
So that's actually one of the core strengths, in my opinion, of PyTorch Lightning, is because of the way that you have the specific PyTorch Lightning, the PyTorch Lightning interfaces for your Lightning module and your data module when you need to combine things. So for example, if I have a image classification task, or and I want to run it on a new data set, right? Or I want to take multimodal inputs, I can more easily configure it to swap things out. I also get the flexibility of being able to leverage at the end of the day, like PyTorch Lightning, the interfaces are designed so it's organized PyTorch code. So you have all the flexibility, even though, for example, like it will abstract out your ability, abstract out you having to do optimizer and optimizer.step, for example, in your optimization step, if you don't want to mess up there, because a lot of people make that mistake, they forget in their code to write optimizer.step. If you need that flexibility, if you need to go to the level of AutoGrad, or even do things like we have Ananya, who's a research engineer, is working with self-supervised learning and do some really cool, amazing stuff with that. Like you can open it up, and it really does provide research flexibility and reproducibility in a way that is much more difficult with vanilla Lightning, vanilla PyTorch. I'd also say I'd go one step forward. It's like our community is kind of showing this to us. So like pretty much from what we've seen, like all the top research labs use PyTorch Lightning. If we look at our downloads over the past 2 months, we went from 1 million to over 3 million downloads in the past, and it's been 21 months, and we went from like 0 to what is it like now we're at 14,506 stars, and we have pull requests and an active community of over 500 to 600 active contributors, and as well that we have a really active community on Slack. So that's one of the things I also love about the PyTorch Lightning ecosystem. When you have research challenges or you want to do something in a new, interesting way, there's like a dedicated community, PyTorch Lightning experts that are available, that are on call every day, every hour of the day. And they help guide you in the direction you want. So what's nice about that is, so that gives you the ability to organize your code. And then on the grid side, the vision on the grid side is from there, you'd still need to manage your infrastructure. How do you scale that code? Where do you run that code? How do you manage that? If you want to, with Grid, that gets optimized and configured out of the box, so that enables you to scale without having to worry about all the overhead of local configuration of your environment.
I had a question on, so I noticed that on the website that it seems like you're able to use your own company cloud or your own like research lab cloud and keep all the data and compute there instead of like using Grid's resources necessarily.
Yep.
I was wondering if you could like talk a little bit more about that relationship, and also like yeah, or I guess maybe start there.
So I actually, for me, that answer, and Armin, I'm sorry to put you on the spot, but I actually think like Armin has to answer that question almost every day. So you want to take that one?
So depending on where your resources are, you can run it on an on-premise environment, and you can also run it if you're using a VPC, for example, say AWS, for example. If you wanted to run it in your own VPC, you could do that as well. Then the third option is you can just run your models in the Grid community. So we try and give you, depending on how you want to deploy, various options, and depending on what you're looking for as far as like size and compute machines and things like that, we can work through those with you as well.
Gotcha.
Did that answer your question?
Yeah.
So one of the problems I have faced while in research especially.
Let me take a step back. What kind of research are you doing?
Oh, so I'm not doing right now, but I was joined as a student, but before that I was working at NTU as a researcher. Okay. So there I was working in person identification and mainly computer vision applications.
Okay.
And object detection. So I was trying and playing around with self-supervised models lately. And so whenever we're trying to make a new model or anything, and we like how you showed like where you get the boilerplate errors and all.
Yes.
Those are a lot. And usually how we solve that, we use metrics, right? We use metrics and visualization to help us see like if a code is running right or not. So one of the major problems that I have faced is like, okay, I developed the code and it's working, like the loss is going down, it's optimizing, everything is working, but I still don't know if it's doing the right thing that I wanted to do or not, right? And why it's doing like more on the explainability side.
Yes.
But so what I used to do is I used to like have checkpoints after every code or something, and whether I can have an output after every epoch or something, like okay, how is my activations being done and everything. So is there anything those visualizations being in Grid.ai?
Yeah. So it actually comes from two factors. So yes. So what's nice about Grid.ai is everything that you would do through, for example, like TensorFlow Logger or traditional logging for visualization that can be visualized in anything that can come through the logger can be visualized in Grid.ai. And then on the other side of things, what's really nice is that's where this open source ecosystem is so great. Because Grid.ai is really about ensuring that you can get the best practices without having to do all the manual configuration of the infrastructure yourself. The idea that we talked about is let's decouple the infrastructure, the ops, from the actual machine learning process. But where the actual machine learning process comes when we're talking about preparing metrics, like that all happens in the open source ecosystem. And that's why I love my job. I'm an open source engineer. I love working with open source. So that's where things like Torch metrics and the integrations with the PyTorch Lightning loggers and the work that we do with all sorts of companies like conversations like with companies like Weights and Biases and the rest, like that's where as an open source ecosystem we can come together and really push everything forward. So what I would say is like solving those things, that's where we do in open source. And then when it comes to actual visualization, instead of you having to do all this extra work to support that open source, the goal is that you can focus on the actual machine learning and not have to worry about all the configuration at the environment level and setting up so you have the logging visualization. We should handle that. That should work for you so that you can focus on getting the metrics that you need to actually identify whether your self-supervised model is working or if your loss is just falling for some non-related reason because validation loss isn't a good indicator of some whatever model that you're using. So cool. Do we have any written questions or are we?
We don't currently, no.
Okay, awesome. So I'll probably at this point, if there's additional questions,
Wait,
yes.
one came in, so
Cool.
do I have to have my training data on your platform to use your training sessions?
So my understanding is it depends on the use case. That's number one. So if there's a specific use case, please reach out to us because we have different tiers. At the community tier, the data goes into the data, or you upload the data into the data store. That being said, there are other, so I do believe to run things that you do have to have the data on the community tier. Armin, you can correct me if I'm wrong about that, but there are potential other options. So depending on your use case, if that's something that's really interesting to you, please reach out to me on LinkedIn or in the PyTorch Lightning Slack. My name is Ari Bornstein, ARIBORNSTIN, and I'm happy to try to identify, depending on your use case, what we can do and how we can make things work for you. So perfect.
Great.
Awesome. All right. So I think we can probably end the recording then, and then we got some water and soda, a couple snacks, and happy to talk and get to know you guys a little bit better. Thanks to everyone who attended.
Thanks, Ari.